Ever wonder how your computer actually gets what you're trying to do? I mean, we type words, we click on pictures, we listen to music, but under the hood, our devices are speaking a totally different language. Today, we're going to decode those fundamental languages that really power our entire digital world.
So here's how we'll break it down. We'll start with why we even need a translator between us and our machines. Then we'll dive right into binary, the computer's native tongue, and see how it stacks up against the way we count, the decimal system. After that, we'll check out a couple of handy shortcuts for programmers, and then we'll put it all together to see how these 4 different languages are actually just one big, beautiful system.
All right, so the problem at the heart of it all is pretty simple. Humans and computers just don't speak the same language. Not even close. Everything we do, every single action has to get translated.
Let's think about a super simple action. You're at your keyboard and you press one key. Let's say the capital letter A. The A pops up on your screen. But what really just happened inside that box? How did the machine understand that specific command? Well, here's the thing. Computers don't see an A, they don't see images, they don't hear sounds. They only see numbers. Everything, and I mean everything, gets translated into a numerical language that's built just for them. To your computer, that letter A is nothing more than a specific sequence of numbers. So, what is this special native language? It's called binary. And it's built on the simplest idea you can possibly imagine: on and off. The clue is right there in the name. Think about the prefix bi, like in bicycle. It just means 2. So the binary system is what we call a base 2 system. It only has 2 digits to work with, a 0 and a 1. That's it. The entire digital universe is built from just those 2 numbers. Now, the real power of binary is how perfectly these 2 digits connect the physical reality of electronics. See, a computer is just a collection of electrical switches. So a 0 can represent a switch that's off, no electricity flowing. And a 1, well, that's a switch that's on. It's a simple no or yes, false or true. It is the most basic, fundamental way you can represent information. Okay, let's go back to our letter A. The computer sees it as this string of 8 digits, 01000001. Now, each spot in that string has a specific value based on powers of 2. You can think of it like a row of light switches. We only care about the switches that are flipped on, the positions that have a 1. In this case, there's a 1 in the 64 spot and another 1 in the 1 spot. You just add them up. 64 plus 1 gives you 65. And in the computer's universal codebook, known as ASCII, the number 65 just means the capital letter A. That's the translation, right there.
By the way, these individual zeros and ones have a name. We call each one a bit, which is short for binary digit. And when you group 8 of them together, like we just did for the letter A, you get something called a byte. And that is the fundamental building block for pretty much all digital information.
Okay, to really wrap your head around how computers count, it's actually super helpful to take a quick look at the system we humans use without even thinking about it, the decimal system.
And just like B meant 2, the prefix deci means 10. You see it everywhere, right? A decade is 10 years. A decagon has 10 sides. Our number system is a base 10 system because we use 10 unique digits, 0 all the way through 9.
Now, just like binary, our system is all about position. Take a number like 1,243. We know the 3 is in the ones place, the 4 is in the tens, the 2 in the hundreds, and the 1 in the thousands. Each spot is just a power of 10, you see? It's the exact same principle we just saw with binary. The only thing that's changed is the base number.
So computers speak binary, and we humans use decimal. But people who work with computers all day, programmers, engineers, they often use 2 other systems. Not because they have to, but because they're a really convenient shorthand that makes their jobs a lot easier. They're called octal and hexadecimal.
First up is octal, and I bet you can guess this one. Octa, like an octagon, means 8. So this is a base 8 system. It only uses 8 digits, 0 through 7. It's just a more compact way of writing out long strings of binary code. And then we have hexadecimal, which is everywhere in programming. Its name is actually a really clever hint. Hex means 6 and deci means 10. Put them together, 6 plus 10 is 16. It's a base 16 system. But wait a minute, we only have 10 digits, right? 0 through 9. So how does that work? This is where it gets pretty cool. To get the extra 6 digits it needs, hexadecimal just borrows the first 6 letters of the alphabet. So an A stands for the number 10, a B is 11, and so on, all the way up to F, which represents 15. This lets programmers pack a lot more information into a single character, which is incredibly efficient.
Okay, so we've just talked about 4 different number systems: binary, decimal, octal, and hexadecimal. They look different, they feel a little different, but the big secret is that they are all built on the exact same foundation.
It all boils down to one simple concept: the base. Binary is base 2, octal, base 8. Our everyday decimal system is base 10, and hexadecimal is base 16. That's all it is. The base just tells you how many digits you have to play with in that particular system.
And that brings us to the single, unifying idea, the key that unlocks all of it. No matter what system you're using, the value of any single digit comes from just 3 things: what the digit is, where it's sitting in the number, and what the base of the system is. Once you get that, you get all of them.
And that's really how it works. These digital translators are constantly working, turning our complex human world into a massive series of simple on and off switches. It's an incredibly elegant and powerful system, which kind of leaves you with a big question. If this entire complex digital world was built on just 2 simple states, what in the world comes next?